going over gray code and then K mapping, and I know this is a little different format than what I normally do, but I'm going to show you some concepts on here, then we're going to implement them in VHDL and put them onto our FPGA. So let's start with gray code. To actually generate gray code, we're going to start with a 0 and a 1, and the thing about gray code is, unlike binary, if we have 0, 0, 0, 1, 1, 0, 1, 1, if we look from here to here, there's one change in bits, but then this has a change and that has a change. So there's from here to here, there's two changes, and then from here to here, there's one change. We only want, in gray code, one change to happen every cycle. So to generate one bit change at a time, we're going to start with a 0 and a 1, then we're going to mirror this over that line and have a 1 and then a 0. We're going to pre-append zeros up here and pre-append 1s down here. Now we've generated the 3-bit gray code, or a 2-bit gray code, and you can see that from 0, 0 to 0, 1 there's 1 bit change. From 0, 1 to 1, 1 there's 1 bit change in the first position, and then from 1, 1 to 1, 0 there's 1 change right here. So that doesn't violate anything. So we move our line down here, and now we'll mirror 0, 1, 1, 0 over. So we have 0, 1, 0 like that. It just mirrors exactly over. And we have 0, 0, 1, 1, which will mirror 1, 1, 0, 0. Now above the line we append zeros, and below the line we append 1s. And now if you look, every bit pattern is only off by 1 bit position. So you can see here we have 0, 1, 0, this is 1, 1, 0, the bit changes on that bit. Then from here to here the bit changes on that bit, and then from here to here the bit changes in the middle, and from here to here the bit changes on the end. So gray code is very nice because it has 1 bit change per position. We need gray code. So I'm going to implement a sum of mini-terms equation, and it's basically going to be, we'll use a 3-bit equation. So we're going to have a function of A, B, and C. It's going to equal to the sum of the terms of, and we'll do all the odds. So we'll do 1, 3, 5, and 7. And I'll show you why we're going to do that. So this is basically saying we have a 3-bit number, and we're taking the values, the 1 that is 0, 0, 1, then 3 is 0, 1, 1, 5 is 1, 0, 1, and 7 is 1, 1, 1. This corresponds to not A, not B, C, plus not A, B, C, plus A, not B, C, plus A, B, C. So that's what that equation translates to from our inputs here. So A is always our most significant bit, or that's our MSB, and this is our LSB, which is our least significant bit. So to see how we can simplify this equation, because this is something that actually is quite familiar to us, but we'll see in a second. So how do we simplify this? Well, we're going to erase that, and we're going to make a K-map. So K-map, we're going to put A here, and BC here, and we're going to draw a line like that. So A can only have 2 values, 0 or 1. BC can have 4 different values, 0, 1, 2, and 3. So we got to make 4 spots like that. But here's where the gray code comes in. It goes 0, 0, 0, 1. We don't want 1, 0, we want 1, 1, because it's a 1-bit change. And then we'll have our 1, 0. So then it helps to come in here and write our numbers in here. So we have a 0, a 1, a 3, and a 4. Then we have a, oh, not a 4, that's a 2. Then we have a 4, 5, 7, 6. So now whenever we have a number here, we just plug in a 1 here. So we don't have a 0, we have a 1, we have a 3, we have a 5, we have a 7. We see that our 1s are grouped in a pattern right here, so we can circle them. And then say, since it's taking up both A, we know A is a don't care. So we're going to have X. But then it's taking up this and this here. So we're looking for the change in bits. And so the change in bits is in our B, because C is constant. So then we're going to say, this is just X. C, because A takes on both values, B takes on both values, and C stays as positive. So this is also just equal to the input C. So this equation here, where we had 001, 011, 101, 111, and that translated to not A, not B, C plus, not A, B, C plus A, not B, C plus A, B, C. That whole thing is simplified to that expression there. And so that's why K-map's useful. So we'll go over one more example after this. A similar example, but in this time, with our sum of our minterms, we're taking the evens instead of the odds this time. And then I added on this part here, which is the sum of the don't care variables. So if you have a don't care variable, you're going to end up putting x's in your K-map instead of 1s, which is saying you don't need to use it, but you can if you want it to be, if it helps simplify things. So our don't care values are going to be these two odd numbers there. So we're going to plug in a 1 in our 0, in our 2, in our 4, and in our 6. So we get that. Then we're going to plug in x's here. So now here's the thing about a K-map. This K-map can be seen as a torus with values on it like that, and here'd be 0, 1, 3, 7, whatever, or 0, 1, 3, 2, and then this would be 4, 5, 7, 6. So you have to imagine it loops around and around like that. So it's like a 3D shape almost that you can imagine. So the way we can simplify this is we can take these 2 bits this way and these 2 bits this way, and that makes a circle. So we grouped these. So we're done. But if we wanted to, instead of having an x here, if we had a 1 here, so if this was changed to this and we added a 7 on here like that, so now we have a 1 here, this doesn't satisfy the K-map. So now we can take the x in that, but when we do a K-map we want to take the group of the largest size that we can do. So we can double up and take this whole thing also. So when you do this, you're going to have a sum of a sum of terms basically. So if we look at this first circle that goes off to the edges, A is taking on both values, so there's an x for A. Then we have B is 0 and B is 1 here, so B changes, so you're going to have a B, and then C stays at 0 on the edges, so we're going to have an x. So it basically just transfers to B. No, I'll write it down here, B. But then we're going to have B plus this other circle that we made. So this other circle that we made takes on both values of A, so there's no A. It takes on both values of C, so there's no C, but it only keeps the value B, which is true. Am I saying that right? This takes on A, this takes on, so it's C, the first one is C bar. Then the reason being is that's a 0, that's a 0, that stays the same. So when it's 0, we take the inverse of C, which is C bar. But this is 0 and 1, so it takes on both values of B, and it takes on both values of A. So we got a value of not C for our first circle. And for our second circle, we're going to have a value of B, because it takes on both values of A, takes on both values of C, and only has a positive B component. So this expression up here got simplified to this expression here. If we didn't have this x, if we weren't allowed to use that, then we would have to group it like this. And so then instead of just B, it would have been B with another value onto here. So it would have been a little bit more complicated. So, but since we had the don't care, it was able to be simplified a little better. An example where we have a 4-bit input. So that means we have a 4x4 K-map, because 4 bits creates a 16 outputs. So we can see here in our K-map, our gray code goes 0, 0, 0, 1, 1, 1, 1, 0, and then down the line it goes 0, 0, 0, 1, 1, 1, 1, 0. So when filling in the numbers for this K-map, it goes 0, 1, 3, 2, 4, 5, 7, 6, because of the 3 and then a 2 instead of 2, 3. But then we notice that we have a 3 here and then a 2. So we have to go from this line to this line. So we have 8, 9, 11, 10, and then we come up to here and we get 12, 13, 15, 14. So that's the way the K-map gets laid out when you have a 4-bit input. So now you can see that I have a min terms of 0, 1, 2, 4, 6, 13, 14. So we're going to go ahead and fill in ones where we see values. So 0, 1, we have a 2, 4, we have a 6, and then we have 13 and 14, just like that. Then we have in our don't cares, which are 3 and 5. So now, what is the easiest way to do? Well, we can take this group here, which includes this one. We can take this group here, and we still need to get this one and this one in here somehow. So the only way for us to do that is to circle this like here, and to circle this like this. So now we're going to have, since we have 1, 2, 3, 4 circles, we're going to have 4 terms being added together. So let's first see what happens. So this circle here takes on values of 0, 0, 0, 1. So it doesn't change is the A. B takes on both values, but A is 0. So we're going to have A bar. Then we have 0, 0, 0, 1. The C stays at 0 and the D changes. So then we're going to have C bar. That's our first term for this circle. Then we have the circle that comes off this way and that way. So that has terms 0, 0, or we'll work with AB first. That has 0, 0 and 0, 1. So what doesn't change is the A. So we're going to have A bar again. And this time we're going from 0, 0 to 1, 0. D is what stays the same, and D is off. So we have that. Then we're going to have 2 more terms now that are a little bit larger than this because it's only 2 circled. So now we have something that's taking on the value of 0, 1 and 1, 0, or 1, 1. So what's changing here is the A, and the B is positive. So we're going to have B. And then here we have 0, 1, so it only takes on 0, 1, so that means it's C bar D. And then we're going to have, for over here, we're going to have it taking on the same thing. It's going to be B also because A is taking on both values, B is taking on something. And it's a 1. And then we have a 1, 0 here, which corresponds to C D bar. So now if we take all these terms and add them together, we get AC plus AD plus BCD plus B, A bar C bar plus A bar D bar plus B C bar D plus B C D bar. And that's the simplified expression from this. Whereas this you could implement with a decoder, just with the outputs of the decoder going to the output of the total thing. You just OR those together. But this is a simpler expression than a decoder that's 16 bits long. Or 4 bits long and has 16
Okay guys, so here I am inside Vivado, and we're going to go ahead and write some VHDL code to implement that last K-map that we did. So the 4-variable K-map we're about to implement. So how we do this is we're going to go into File, and New Project. We're going to specify a new Vivado project. We're going to name it 4-bit K-map. Cool. Do not specify sources at this time. Okay, so my board is the 236 TAC 1. It happens to be that guy right there. So that was just picking my FPGA board that it'll try to mount to. So I'm not going to try to close out of my old lab. I'm going to use that kind of as a way to check what I need to do. So first we're going to do is we're going to add sources, and we're going to click Add or Create Design Sources. We're going to have to create a file, and we're going to put it in VHDL, and we're going to call our file Actually, we're going to have a problem because I named the project with a number. So we're going to call this 4-bit K-map. Okay. And we're going to cancel here. So we're going to file, save project as. We're going to have to name this 4-bit K-map because we can't have a number. So now that that change to that. Now we'll add our sources. So yeah, now we want it in VHDL, 4-bit K-map. Okay, so now we're going to create our, cancel. We're going to finish, and then it's going to ask us, so this source that we added, we need inputs and outputs to the board. So we're going to need a 4-bit input, and we're going to need a LED output to let us know if, when we entered whatever our bit pattern was, it'll output a 1. So basically we're going to call this 4-bit in. It's going to be direction in, it's going to be a bus, and it's going to be 3 down to 0. Now we're going to add something else, and we're going to have our output, and that's going to be our K-map out. The other thing I want to do is design a decoder as well. So we're going to have K-map out and decoder out. And that's going to be out. And that's just also going to have a 1-bit output. So we're going to see if the decoder output that we build is the same as the K-map output, which they should be. So we're going to say that's good enough. So now we're going to come into our source file here. And we're going to see all this. I'm going to delete some of this so it's easier to see what's going on. I'm going to delete some of this because we don't need any libraries for this. So we can see here that it says entity 4-bit K-map. It has 4-bit in, K-map out, decoder out, and it tells you that this is a standard logic vector that's 3 down to 0. So then it says in here, architecture of this is, and then begin. So what we have to do is specify how we want to start this. So we're going to begin our code underneath this begin statement and before the end behavioral statement. So we basically want to take our 4-bit in and figure out what the decoder for it would be, and then we're going to show that our K-map solution is the same output as the decoder. So we're basically going to say temp is going to get actually hold up, we're going to so actually the way we're going to do this is we're going to say decoder out, which is what we defined up here, which is a 1-bit output, is going to get the output of, and we'll do it like this, decoder out is going to get 1 when we're going to need this in. It's going to get 1 when 4-bit in is equal to 0, 0, 0, 0. Else so we got to change this to that. Then it says else. So we only wanted ones for 0, 1, 2, 4, 6, 13, and 14. So we're basically going to copy this format here. Then we're going to Control V, Control V, Control V. So we had 1, 2, 3, 4, 5, 6, 7 terms. So 1, 2, 3, 4, 5, 6, 7 terms. And we're going to tab these over a little bit. Tab that over. Just like to format things a little bit. So we want a 1 to go to the decoder output whenever we get a certain input. So we want a 1 when we get a zeros, we want a 1 when we have a 1 as an input, we want a 1 when we have a 2 as an input, when we have a 4 as an input, when we have a 6, when we have a 13, which is 8, and and 4 to make 12, and we need a 1 to make 13, and then when we want 14, we want an output. We also want an output on 3 and 5, but we don't really care if it has an output or not. So we're gonna still give it an output on 3. And 5. Alright, so now, actually we don't want that output. It was a don't care condition, so we don't care if that output is there or not. So we're going to delete that. So decoder out, when we get those inputs, should get us that. But then our K-map out should just get, should just have we have a 1 when 4-bit in is equal to, so AC, or A bar, C bar, so that's 0, 1, 0, actually hold up one second. So I'm back, and so I changed up some stuff a little bit, but it shouldn't be too tricky. So here I defined signals A, B, C, and D, and they're type STD logic. They aren't a vector, they're just a single bit. Then I have the decoder out. All of this is familiar, except for these last 2 lines right here, which I had to add because we have the don't care conditions of 3 and 5. So we don't care if we have a 3 or a 5, we want an output no matter what. So that means output when there's a 3 and output when there's a 5, also output when there isn't a 3 and output when there isn't a 5. So that's how we take care of that. We have an output when there's a 3 and an output when there's a 5. So now these signals that I defined will come in handy over here, and we'll define A as the 3rd bit of the input, we'll define B as the 2nd bit of the input, C as the 1st bit of the input, and D as the 0th bit of the input. So that makes doing our logic a lot easier. So in on the blackboard, when I was doing my math, I have it A bar and C bar, where that is wrong. It's supposed to be A bar and B bar. Then the next term is A bar, D bar. Then the next term is B, C bar, D. And then the next term is B, C, D bar. So if we look over here, we have not A and not C. That can just be changed to not A and not B. So we can go ahead and get rid of it like that. Let's make sure our parentheses line up. Then we have not A and not D, which is good. Then we have B and not C and D. And then we have B and C and not D. So we should be able to go ahead and synthesize this now. And this is sending out to the K-map output, that equation. So when this is done and pushed to the board, I'll show you what the output is. Board out. This light over here is our K-map output, and this light over here is our decoder output, so they should match. So we should have 0, 1, 2, 3, 5, or 0, 1, 2, 3, 4, 5, 6, 13, and 14. Those should all provide a 1 on the output here. Anything else should provide a 0, because our don't cares are 3 and 5. So we're at 0 and we get an output. 1, we're at an output. 2, we're at an output. 3 was a don't care condition, so we don't. If we have it or not, we want an output. So we have a 3, so we want an output. 4 was one of our standard conditions, so that works. 5 was one of our don't cares, so whether we have it or not, we want an output, so that's working. And 6 also is one of our values. We do not have a 7. We do not have an 8. We do not have a 9. We do not have a 10, or an 11, or a 12. We have a 13. We have a 14. And we do not have a 15. So there's that implemented both in K-map and decoder style on the board so that you guys can see that the outputs match. Thanks for watching.